Hey, it's okay. How are you?
I can. Do you hear me?
Yeah, now I do. How are you?
Good. Fine, thanks. How are you?
Yeah, good. Thank you. Good to see you.
Very nice. I'm not sure I can share the screen yet, but hopefully it will come. How are things?
Yeah, not too bad. Thank you. Not too bad. Getting better. I guess the same with everyone. How are things with you? Things start to calm down a bit.
Yeah, it's more or less everything is going sort of in both directions, if you know what I mean.
Yeah.
So it's
Hopefully we can soon meet again in person somewhere.
yeah, this will be. I think it will come soon, unless there will be other bad things going on now. But I hope this is still will be better. As with virus, it goes away. Bad things go away sooner or later.
Indeed.
The world will not allow to do this, to happen anything bad, I'm sure.
And in the meantime, it's nice to catch up with friends over Zoom anyway. So.
Yes. I see Seti is coming. Yeah, hi Seti. Nice to see you.
We met, I think, 2014 or so. Yeah.
Okay. Can I try to share my screen?
Yes.
So that everything is sort of. And then I just start like this. So do you see my slides?
Yes, we do see it, yes.
Good. Okay, very nice.
Forward, backward, something like that. Next slide. Something like that to check.
Let me check whether I'm there. Yeah, it should go. Yeah, it works. What I find a little disturbing is that whenever somebody comes into the room, there is a signal, and it sort of tells everybody that somebody is joining. But it's not a problem now. But when it happens, then
during the talk, I think we are muting that from our end, so we should.
Very nice. Good.
Jaime is also expected to join now, so I don't see him here.
I haven't seen him yesterday either, but I talked to him last week, so I think he should be available.
Okay. I mean, EA speakers, we can directly call them and then remind them, but foreign speakers, we don't have any mobile phones or something like that to call. So sometimes these mails are going into spam. That's another big headache.
I mean, unfortunately, I'm missing a lot of talks because of the time shift. So I could not wake up, of course, at 5 or today or something like this. Did Adam give a good talk today?
Yeah, he gave a very nice talk. The only thing is that with the US people, we have to give them the talk either in the early morning or first talk and then last talk. In the middle, we can give. Then it becomes midnight to them.
I see. It's always a compromise. I mean.
Yeah. And even for you people also, we have to find from 3:30 onwards. If it is like Indian IST, if it is below, then yeah, you cannot. It will be too early for you.
So you will let me know when I can start.
Just in a week we can start. So incidentally, it happened that I'm going to chair this session. I requested Carlo to chair, but yeah, he has to travel in the middle. I think he can attend the talks, but he has to leave in the middle. We stop. I'll come back to the post-one session. So now we will be having mostly ARPS talks during this session. We will be having 3 talks. One given by Professor Sergey Borussenko and Professor Phil King and Dr. Jaime Barriga. We don't see him yet, but yeah. First, let's start with Professor Borisenko. Just a small disclosure, certainly we will be recording these talks. If you are uncomfortable, recording in the sense like later on they will be available in YouTube. If you are uncomfortable with that, then we don't record your talks. Is that okay?
Yeah, it's fine. It's fine. You can record.
Okay, then please go ahead. So, it's Sergey Borisenko is from IW Western. He's a group leader there, and he's heavily experienced in RPS. So today he's going to talk on isolator four-fold Fermi Bismuth killer in IO. Please go ahead.
Good afternoon, ladies and gentlemen. First of all, I'm very grateful to Professor Sethi and to other organizers for letting me speak today to present our results. And this is a nice meeting. I learned a lot already from the previous talks. What I'm going to talk about today is our new view on bismuth tellurium iodine. But before I go to this, I would like to show you what slicing onions and doing ARPAs have in common, apart from breaking us to tears sometimes. This is my view of how we collected the data for the Fermi surface mapping earlier. And if you consider onion as the k-omega space with two dimensions as angle along this arrows and energy vertically, then in order to get the Fermi surface in a conventional way using the hemispherical analyzer, one has to first collect what we call vertical cuts. So one has to, this is analogous to slicing onion in this direction. And then in order to get the Fermi surface, you have to put these slices together. And only then you can cut the distribution which you obtain and get the Fermi surface. This is not always practical, and what I always wanted to have is to have the possibility to do the Fermi surface mapping like this, so you can do it at once. And of course, having such a possibility, and this possibility now exists, and if you remember the cooking shows where people be slicing onions with a very high speed, you can collect the Fermi surface maps as a function of photon energies. And this possibility gives you direct access to the mapping of a three-dimensional Fermi surface. And this is example. The data were taken at Bessie. We measured the approximately 100 Fermi surface maps within the 100 minutes, meaning each of these maps took sort of 1 minute. And then you have access to the three-dimensional Fermi surface, which you can then compare to the DFT calculations and consider all details. This is also practical for the experimentalists from the point of view that when you have unknown material, it's not always clear which photon energy is more suitable for that. So very quick scan through the photon energy allows you to see which features are available, which geometry is available, and is favorable for your experiment and so on. So this way of collecting data became possible because we patented a novel technology, which is surprisingly very simple. What we use is the usual conventional electron lens, which does a Fourier transform, meaning that all electrons which left the sample at a particular angle will be focused at a single point at the detector, and those which left a different angle will be focused at a different point. And this has been used already in conventional analyzers. What is new is that in this case, we use the surface of the detector to repel the electrons which we do not need. Basically, two slow electrons. So with this, we do low pass filter which means that we can detect only electrons which have energy more than particular ones, which is said by the repelling voltage of the MCP in this case. And this is illustrated by the red beams showing that the electrons which do not have sufficient energy are just reflected back. With this technology, one could one could see the Fermi surface live on the screen. I will show it later on. The system has an isotropic angular resolution, so you do not to have to integrate your signal within the entrance slit. So you basically see the two-dimensional distribution at once. You have many other advantages. One of them is that the instrument is very compact. This is the promised view of the Fermi surface live on the screen. This is a real-time video, and the bismuth telluride can be watched directly. And this is the more or less stable situation, stable on the scale of hours, but you can track the development of this Fermi surface on the scale of basically seconds. We were very surprised that after the very fresh cleave, you see the Fermi surface immediately after seconds after the cleave, and we were surprised to see how the Fermi surface can change within a minute after the cleave. So these opportunities, of course, expanded the possibilities of the photon emission. Apart from the different photon energies, and we tested the technology already at different synchrotrons, you could do the very fast measurements of the Dirac signal. So since the conference about topology, the meaning of this for the topological material is also very high, because, for instance, you are interested in a very quick estimate of your spin texture of the topological surface state. So this experiment lasted in total 1 minute, 30 seconds for this map, 30 seconds for the other one, and then you see the circular dichroism, which is very clear here. The same holds for very precise measurements of the temperature dependence. So, for instance, you have you want to track how your Fermi surface changes as a function of temperatures, and nowadays it's not a big surprise. And in this particular case, we considered the Fermi surfaces at 2 different temperatures for the lithium iron arsenide, and confirmed our previous measurements, which showed that the Fermi surface shrinks as a function of temperature when it crosses the superconducting transition. And you change only one parameter, of course. So the time after cleave, I already mentioned, this is a larger time scale, but nevertheless, you can track it basically every second and record these changes in big detail as a function of time. Also important, the position at the surface. It turned out that even the perfectly looking cleaved surface of, in this case, bismuth telluride, visually gives you the possibility to see that when you move the sample only a little bit, you could see that the Fermi surface is actually different. And in this case, you moved it by a couple of microns. You can by 10 to 100 microns, and you see that the Fermi surface is different. Finally, you can do the measurements of different Fermi surfaces for the different materials. This is obvious. Not only momentum distribution can be recorded, one could do the energy direction as well. And this is but one needs one additional step. Additional step is you need a differentiation, because when you set the threshold energy at the detector, then you can you're collecting electrons having energies above these threshold energies. It means that if you're interested in the momentum distribution of these electrons as a function of binding energy, you could reduce this threshold energy and then record the integrated spectrum. Then another step which you need to do is to differentiate the data set along this direction. And then you get the dispersion of electrons as you used to have it in a conventional analysis. So this additional step is just, alternatively, you can record the data in a lock-in mode, and then like in tunneling spectra, you could see directly the derivative. This is, in this way, you can record, of course, a lot of data. You could see the full k-omega space within a pretty limited amount of time. The difference, again, is that you have the momentum distribution and not momentum energy distribution as in a conventional analyzer. So these are different topological material where you could see the cones of the topological state, and using actually helium lamp in your lab so that you don't need to go to the synchrotron. The resolution in terms of energy is not a record one, but this is still pretty decent in order to see the opening of the superconducting gap. For instance, in Bisco overdoped, single crystals of Bisco, you could see the opening of the superconducting gap of the order of 11 millieV. You can track the shift of the leading edge, even in the lithium iron arsenide, where the superconducting gap are an order of magnitude smaller. So this instrument is now available. Before I go directly to the data about the bismuth and about our point of view on bismuth tellurium iodine, I show you what we have contributed to the topological zoo, which I like in one of the yesterday's talk, the name for the variety of these materials. And of course, the variety is very big, and we learned from the last talk yesterday that this is now a matter of many thousands materials. And of course, one keeps inventing, they keep discovering them perhaps on a weekly basis. But and we have done this as well. So we suggested different materials also from the theoretical predictions, also from our experimental point of view, among them the 3D Dirac summer metal or the first weak topological insulator, but some more exotic things like non-magnetic half metal or type 2 magnetic wild summer metal have been suggested. But what I see problematic in a variety of topological materials is that the topological features are situated in most cases far away from the Fermi surface. This is a problem number one. And the problem number two, even if they're close to the Fermi level, there are other features which stay on the way, sort of. They will define the properties, they will define the transport properties of the material. And this, of course, makes it difficult to see what comes out from the topology itself. So from this point of view, we paid our attention to this material as it was very known, but so far not topological, in the sense that it has got the huge spin-orbit interaction, and probably the resurrection of interest can be dated by the 2011 after this paper, where the spectrum showed that there are states which looking like Rashba-like, and this was attributed to the bulk bands of bismuth BTI. Soon after that, of course, the resistivity always shows that it is a metal, right? But the common wisdom was that it is a polar semiconductor. We have, soon after this paper, there were other reports, ARPAS reports, saying that actually these are purely surface state. And here is the beautiful data from Phil King's group showing that actually both set of states are present, and actually in a very broad energy region. They interpreted this as a quantum well states. So that we realized that actually the situation in ARPAS community is not that unanimous. There is not a single opinion about that material. Not only in ARPAS, also the Hans von Alphen experiments showed that according to some groups, the material emerged as a essentially three-dimensional material, and the quantum oscillations were originating from the surface state. According to other groups, for instance, this study showed that actually quantum oscillations are originating from the bulk states, and the material is actually two-dimensional and not three-dimensional, quasi-two-dimensional. So we decided to have a closer look at what's going on here. We did the calculations ourselves, and when doing this step, when performing this step, we realized that actually the crystal structure, which is considered nowadays in basically all studies of this material, is based on relaxed crystal structure, not experimental one, but the when one does DFT calculations, the usual thing, when one calculates it, when one relaxes the position of the atoms and does the calculations for the structure. So, but in this case, it's very interesting that experiments actually, not a single one, continuously show that the distance, and the difference is very tiny, the distance between tellurium and bismuth atoms is actually slightly larger than the distance between the bismuth and iodine atoms. And this small difference actually results in a very pronounced difference of the band structure. And thus actually, this is the full characteristic of the material is completely different. In this case, we have a semiconductor with a finite energy gap. In this case, we have a very unique 3D semi-metal in the sense that this 3D Dirac point, we call it also a minimal 3D Dirac semi-metal because the Dirac point is only one, 2 per Brillouin zone, and it's very well isolated from everything which is close to it, right? It's isolated in terms of momentum, and it's isolated in terms of energy, resulting in the what we call Dirac band of the order of 0.4 eV. This would be a very interesting material for the application if this is the case. And actually, the Fermi surfaces from ARPIS experiments, here the Fermi level is drawn according to the common wisdom, to what is more or less generally accepted by the ARPIS community until our study. This is the 3-dimensional Fermi surface. And this is the Fermi surface which is suggested by our studies. So actually the difference is dramatic, but interestingly, apparently, at least we didn't find the Hall effect measurements in the literature, which would show that the charge carrier concentration is significant in this. So let's have a look what ARPIS shows. So first of all, a very rough estimate. This is the valence band on this scale of 5 electron volts. And this is our standard representation. The comparison with the DFT bulk calculations is actually the characteristic feature of my group. We always started to interpret the ARPIS data by considering the bulk calculations. And then if we couldn't explain this data, what could consider surface contributions, matrix elements, correlations, whatever. So this is the first step, and we compare the valence band. And if you compare, these are theoretical bands slightly broadened in order to look like ARPIS spectra. And already at this stage, you see that actually these 3 bands at higher energies are much better reproduced by our calculation than this. So there are surface states, of course, here which are not taken into account neither here nor here. But from this comparison, our alternative view wins. Now coming back to the very famous Fermi surface, which has been measured many, many times by different groups, we call the underlying dispersion as a McDonald's. In this case, it's clear why. This is the Fermi surface taken at 25 eV, conventional energies, and we see basically what other people see. Perhaps one could see additional set of features here, which says that there are more features than just these 2 parabolas. But data set at 15 eV actually was surprising to us because this is a conventional analyzer, but the direction shown by this arrow is actually vertical direction. And it shows that there is a symmetry. And this asymmetry is not expected if these states are just surface states. But again, and this is a pretty clear symmetry, right? Again, the intensity distribution here is a bit strange. There is no distortions because this is along the sleeve. So this is, there's not an artifact. But the intensity distribution, of course, is a little bit unusual, and there are many more features. And the geometry, because here you need to rotate the sample. In this case, we rotated the sample, constantly changing the geometry. So we decided to apply our FSUMA in order to clarify whether this is the case. And indeed, we took the data at 2 energies. We did a short scan, actually rather long scan on the photon energies. We saw the 3D dispersion, which tells us that we are sensitive to the bulk with a conventional energy from energies from 50 to 90. So we are sensitive to the bulk and we see how the bands disperse. We identify the gamma point in a potential. And now we take the data with the Fusuma at gamma point, so 22 eV. What we see exact correspondence with the hexagonal shape, what theory predicts. And this is normal in the gamma point. But as soon as we go away, and this is approximately 10% away towards the R point, A point, we see that the Fermi surface is no longer hexagonal, it's trigonal. And it's just exactly as actually the calculations of the bulk Fermi surface imply, that you need to have the trigonal, and you see that where symmetry comes from. So this is the very typical Fermi surface for the bulk Fermi surface of this material, and it's very difficult to explain it from the point of view of a purely surface state. So that's again, this kind of scenario certainly fits our picture than the old picture. Another thing is that we measured the spectra also using the laser at 5.9 actually 5.9 eV laser, meaning that this is the most bulk sensitive spectra of bismuth tellurium iodine ever measured, because the previous data included the laser data with the 7.7 eV. So this is the lowest energy data, usually considered as the most bulk sensitive. And again, we see two sets of the features, which is in very good agreement with our picture and in contradicting the picture that this is just a surface state. We tried to clip the sample at 10 to the power minus 4 millibar, and we still saw the states as independent on the state of the quality of the surface. So the argument here is that according to the universal curve, you're very sensitive to the bulk using this laser radiation. And you still see the two features very clearly, which then speak in favor that this is not a surface state, that this is a bulk state. Moreover, we have, knowing the 11 eV, we know that this is mostly gamma point. Of course, using the lower energies, you not only increase bulk sensitivity, but also your KZ resolution is a little bit worse, because you are squeezing the momentum scale along KZ, and the mixture of different features is very natural. In this case, it is very natural also because in our picture, if you notice near the gamma point, there is a flat portion of the band, and there is a flat portion of the band near the A point. So actually having two components is very natural in our picture, because you have the two sets which correspond to these two extremes, and these two sets of Rashba-like bands actually should appear in your spectra if you integrate more along KZ. And this is in a very big disagreement with the old picture, which showed that at gamma point there should be nothing. And there is only one set of features around A point, and this should be smeared out by the KZ resolution. Finally, we thought, well, why not to try to detect the 3D Dirac points directly? And then, since we know the inner potential, we did the photon energy scan at the photon energy at the kinetic energy, where we do expect these features. And we saw that using 66 eV, we see the Dirac point. Using 74, you don't. Then you plot it on the map, and you see that the Dirac points are shifted towards A point. It's not exactly as in calculations sitting in the middle, but they are shifted towards A point. But we continuously see that they are present in the vicinity of A point. So we interpret this as having two Dirac points here and here. Of course, we have still moderate KZ resolution, especially in this energy range. So this is all smeared out, but it's consistent with our interpretation, and these spectra represent the bulk dispersion. What does it mean to us? That, of course, having a Fermi level is here, Dirac point is here. Just doping material by holes would be nice to have the great material, but of course it's very difficult. What we notice is that it was also established earlier that there are two terminations in this material, tellurium termination and iodine termination. you cannot get it in ideal single crystal in ARPAS, because when you cleave, you have either or. But in this case, because of stacking faults, you can see both terminations actually. So in most ARPAS studies are concentrated, including ours, on the tellurium terminated surface, because there you have these McDonald's, and with iodine you don't have it. But actually, considering the valence band spectra, we have a feeling that iodine terminated surface corresponds just to the shift of the band structure towards the Fermi level, meaning the Fermi level actually is much closer to the 3D Dirac surface. Therefore, the suggestion would be to stabilize somehow the iodine terminated surface of the single crystal, and this could give the way how to get a stable material with having a canonical 3D Dirac point at the Fermi surface. So at this point, I would like to, and I see my time is up, I would like to thank my collaborators. This is my team in IFW Dresden. These are numerous people from the synchrotrons who helped with the 3D measurements of the Fermi surface. This is our theorist who does the calculations for us, Sasha Reska, and as always, Helmut Berger, who provided the single crystal. So I thank you for your attention, and I leave you with my conclusions.
Thanks, Sergey, for the nice talk. Now the talk is open for the questions. Yeah, Phil, please go ahead. So let's take first online.
Thank you for the very nice talk, Sergey. I was curious about the dimensionality of the state. So you showed this KZ-dependent map a couple of slides back. Maybe you could go back there. Yeah, here. So I mean, if I look at this, I think I can see some states that look 2D and some states that look 3D in there. So do you think you're seeing a mix of surface states and bulk states with that?
Yeah, I think, the surface states are always here. I mean, we have done a lot of slab calculations. The surface states are also present, but we think they are sitting actually here. I showed them in the earlier plot where I showed the valence band, and there was pretty clear the surface state which did not coincide with the bulk bands where we compared. So surface states should be there, but I mean, they are not topological surface states. That's why they're not robust as in bismuth telluride or bismuth selenide. And our experience is that the non-topological surface state could be a very fragile object. They could turn up, they could disappear. It depends on many factors. So
if you take this KZ map that you show on the right at the Fermi level, then do you see all the bands dispersing there as a function of KZ, or do you also have 2D states?
We have a dispersion of that. We showed that we see the dispersion of the size of the Fermi surface also by the 10%. It's in line with this quasi 2D Fermi surface which we have. So because the 3D Fermi surface which we advocate is actually quasi 2D. So this is a different interpretation. So we think that this quasi two-dimensionality, which has been always seen, is actually the evidence, like the Haas-van-Alphen study, the first one showed that actually this Fermi surface is quasi 2D, and that's why these states are bulk rather than the surface.
Great, thanks very much.
Professor Saras Gupta, please go ahead.
Yeah, nice talk. I have a question regarding the difference in crystal structure, which is DFT optimized and experimentally measured, which had a very big influence on this slide. So I don't know, of course, I don't know whether it's really makes sense to ask you this question, because the theoretical work has been done in collaboration with Sasha. But it depends on what kind of exchange correlation and everything. It depends quite a lot. Is the layers, are they, in what way they are coupled? Are they coupled in a van der Waals way, or how are they coupled? Or
I'm not an expert in this. I know that the details of the calculations can change it. I'm aware of other type of calculations in the literature of this material with the different structural parameters, this Dirac point can be shifted to the side. The position of the band strongly changes. That's why I'm always saying, and we do not have a perfect quantitative correspondence. We never have the perfect quantitative correspondence. But this is something which I always use as a rough picture of what's going on. So for me, it was important to see that actually, if one considers the experimental crystal structures, then the agreement with my experiment is actually more reliable than if I consider the theoretical structure. So I cannot tell you the.
I understand as a theoretician why is this big discrepancy, but I can talk to Shasha.
Actually, we're about to post, the paper is submitted, but the preprint will appear in the next day, and there are details certainly.
Okay, thank you.
Professor Dasgupta, please go ahead.
Yes, so this is more of a question out of curiosity. So this is a polar semiconductor, and I think it came into prominence because it shows Rashba effect, right? So you clearly see the evidence of Rashba effect in your photoemission spectra.
I wouldn't call it. Well, we can call it Rashba-like states. This material is a non-centrosymmetric material with a huge spin-orbit coupling.
Yes.
So the bands look like this. If you want to call it Rashba-like, you can call it Rashba-like. But for me, it's not necessary. It's not necessary thing to do this. I just consider straightforwardly non-centrosymmetric material with a large spin-orbit splitting. Okay.
So is there a way to find out from your photoemission or RPES in case of splitting whether it's a Rashba kind or anything of that, Dresselhaus or something of that kind?
We see this kind of spectra. If they look like a Rashba split bands to you,
yes,
we can call it Rashba, but this is a matter of terminology. For me, it's a bulk bands of non-centrosymmetric material with a large spin-orbit coupling.
Okay, excellent. Yeah, thank you.
Okay, are there any questions offline? Okay, then I have a technical questions. Okay, so what is this FESUMA? I mean, maybe you have already explained this detector. I think.
Well, it's an instrument which measures ARPAs, which
expansion of that. Maybe you have mentioned. Maybe I did not notice that. So,
yeah, it's a very simple thing. It basically uses the Fourier transform lens as every analyzer, but the field in this analyzer is not the same because there is a retarding field of the MCP, and in this way you can do. You can see the Fermi surface live, and then you can do the differentiation in terms of energy.
I know all this. I mean, I want to know the expansion of this FESUMA, FESUMA.
Oh, this is Fermi surface mapper.
Okay, maybe I think I missed it. So now the question is regarding this. So I see a lot of aberrations on your image. So you have to do back correction, something like that, after collecting the data.
You mean aberrations, which always? Yeah, this is the same as all analyzers. Your focal plane is not a plane, and this is the story for all known to me types of analyzers. We have the same here.
Okay.
So that's why the acceptance angle is limited. That's why we have different modes. But this is always the problem with because your focal plane is not a plane. But the advantage here is that we are using the first focal plane. Hemispherical analyzers use it. That's why the lens is so huge. It does use the second focal plane because you cannot put your hemispheres in the chamber. In our case, the detection of electrons occurs 10 centimeters away from the source, or something like this. Meaning that we also do not have, our trajectories are very simple, which probably plays a good role. We are going to test it with time resolved measurements where we hope to decrease the space charge effect.
Okay, so the pass energy also is the same, similar to like other detectors that we need to select particular pass energy, or?
Pass energy, this is approximation of zero pass energy. We don't have we never accelerate electrons. That's why the theoretical resolution, energy resolution of this instrument exceeds actually those of conventional hemispherical ones, because we do not accelerate in the lens, we only retard them, right? So, and there is no pass energy. We don't need to have a pass energy, because we detect all electrons which have kinetic energy sufficient to go through this barrier to the MCP.
Okay. Okay, thanks. So we have, I think, Carlo wants to ask the question. So please go ahead. Maybe this.
Hi, Sergey. Nice to see you.
Hi, Carlo. Sorry to miss the talk yesterday. I wrote you. I overslept.
It's a very nice talk. I was just curious to know the, of course, this Dirac states that you see. I mean, it shows some photon energy dependence. So probably, but is it the spin characters are also known of those states?
No, we didn't do this, but this has been done before. That there was a spin polarization seen on these states. But I mean, with such a huge spin-orbit interaction,
yeah, okay.
Surprising. But we would like to do it with the laser. The problem is that with FESUMA, the Fermi surface is too large for the laser, and it's not that good.
Absolutely, yeah.
In the bismuth telluride with the laser, it's not. No, it's like this, but okay, maybe we'll do this also with FESUMA to see this the dichroism at least, not spin.
Yeah, because I mean these are layered materials, so maybe the interlayer coupling is not very strong. So that probably, I mean, the reason that even if you have a bulk states that can give you weaker dispersion as a function of Kz, I think that's probably is the one that you are seeing in your experiment. So
yeah, I think.
Yeah, but anyway, it's very nice. Yeah, very nice data. Yeah.
Thanks, Carl.
Thank you.
Okay, so I think next time. So thanks everyone once again for the nice talk. So now the next talk will be given by Professor Filke from University of St. Andrews. He will be talking on bulk and surface Dirac states in tungsten metal dichalcogenides. And Phil, I think it's okay for your recording, right? So you have no problem.
Yeah, no, that's no problem.
Okay.
Do you see the slides okay?
Yeah, yes, we see them. Yeah. Please
Okay.
move them so that. Can you go to the next slide? Yeah, it's now.
So that's working fine, sir?
Yeah, it's working fine. Yeah.
Okay, great. Well, yeah, thank you very much. And I'd like to, of course, thank the organizers for the invitation to join this nice and very interesting meeting. So yeah, I want to stick now with the theme of electronic structure measurements from angle resolved photo emission. And what I'd like to talk about is a rather general mechanism for stabilizing bulk Dirac points of the form we were just hearing about, and also ladders of topological band inversions across the family of the transition metal dichalcogenides. And then I'd like to talk a little bit about how this actually is a key feature for understanding some rather unusual charge density wave behavior in one of the series here. Okay, I should start by pointing out the people that really did all the work here. And this has been a very collaborative set of projects. And in particular, for the topological band inversions work that I'll talk about, I'd like to point out Oliver Clark, who was a PhD student in my group up to a couple of years ago, and who really led a lot of that work. And actually, he's now a postdoc in Bessie working with our next speaker. And for that component of the work, we also had a very nice collaboration with Sahid Baremi for theoretical calculations, density functional theory calculations. And he's now a senior lecturer at the University of Manchester. And I'll also talk about some work on titanium telluride and monolayer systems there. And I'd like for that to really point out Tommaso Antonelli, another PhD student in the group that led that work. Okay, so we've already heard in the conference already about some of the members of the transition metal dichalcogenide family, and I'd like to then continue considering this system here. And for what I talk about today, I'll be talking mostly about the so-called 1T family of these systems, where we have a transition metal that forms a triangular lattice here, and this transition metal sits at the center of a chalcogen octahedron. So just like, say, the perovskite structure, for example, except here these octahedra are tilted over so that they're edge sharing, and then you have these octahedra joined along their edges in the plane. And there's actually a few different structural polymorphs of these transition metal dichalcogenides. For example, in the 2H structure here, you have the chalcogens rotated in the same orientation in the plane above and below the transition metal. And much of what I talk about will actually be general across this class. But the key feature is we take these layers of transition metal chalcogenide octahedra, and then we stack these together with van der Waals interactions between the layers. And I think one of the nice things in this material family is the huge variety of different properties that we find by changing the transition metal and by changing the chalcogen. And so they host very well-known superconducting systems and charge density wave materials. More recently, there's been a lot of interest in the strong spin orbit semiconductors in the family as well. And it's really generally considered that the main distinction between the different members of this family is really driven by the filling of the transition metal d states. So as you start from the group 4 systems over here, where you have the d states nominally unoccupied, and you start to populate these d states as you move across the series. But what I'd like to really focus on for the first part of the talk today is not the d states themselves, but rather the p states that are derived from the chalcogen in the system. And actually, it turns out that these p states can stabilize on their own, if you like, some topological physics in the material, and also are really relevant to understanding some of the collective states as well. And so to begin with, I'd like to think about the group 10 system, palladium ditelluride, which is interesting in its own right. It's superconducting below about 2 Kelvin or so. But it's also really a beautiful model system for understanding the role of the p states in these TMDs in general. And that's because if you take this system, and I'm showing you on the left here density functional theory calculations from Sahid Baremi, you see that actually the weight of the d states is pushed down, a couple of electron volts or so below the Fermi level. So all the states at the Fermi level here are really dominated by the chalcogen, in this case tellurium p states in the system. And one thing that immediately leads to is a rather three-dimensional character of the Fermi surface in this material. Although these are layered van der Waals materials, the chalcogen states are sitting either side of the van der Waals gap, and so there's still finite, in fact quite significant hopping between these states across the van der Waals gap. And that gives us a rather three-dimensional character to the electronic structure here at the Fermi level. And you can see that, for example, in these measurements here performed in the gamma plane of the material, and in the pi/c plane of the material, in the A plane of the material, where you see a rather dramatically different Fermi surface here, governed by these tellurium p states. Okay, so with that in mind, with this thought that the p states here are really the thing that's dominating the electronic structure, I'd like to walk through a really very simplified picture of how we can think about the electronic structure derived from these different p orbitals. And so we of course start with our three p orbitals, our px, py, pz orbitals. And in this system here, these p orbitals sit in a trigonal crystal field. And so this trigonal crystal field will split off the energy of our pz derived state above that of our px and py derived states. Now we're dealing here with tellurium p orbitals, and so we have also a strong spin orbit coupling in the material here. And so we need to consider the influence of that. And that will shift in energy the pz derived states, but also split apart now the px and py states into a pair of states that you can see here. Okay, so this is then our starting point for thinking about the electronic structure. And we can ask how these states should disperse throughout the three-dimensional Brillouin zone, in particular thinking along the gamma A direction, or the 0 to pi/c direction of the Brillouin zone. Okay, so if we first think about these pz derived states, these are states with the lobes of the orbital pointing between the the neighboring TMD layers. And so you can expect a fairly significant interlayer hopping coming from these PZ-derived states. Or in other words, you'd expect there to be a large out-of-plane dispersion of the PZ-derived bands along the gamma ray direction of the brilliant zone. Okay, if we think instead about the PX and PY derived states now, these are our planar orbitals. They're lying in the plane of the TMD layer. And so you'd expect a much weaker hopping of these states across the van der Waals gap. And so this should give us a much smaller bandwidth of these states as a function of the out-of-plane momentum. Okay, and so you see when we have this that quite naturally, as long as the out-of-plane dispersion of these PZ-derived states is larger than the crystal field splitting of the PZ from the PXY pair, then we'd expect this PZ-derived state to disperse downwards and cross through the PX and PY-derived states as a function of the out-of-plane momentum in the system. Now, we also need to remember that we're dealing with a system where we have two chalcogens within the unit cell here, and so we're forming bonding and anti-bonding combinations of these. And this gives us an opportunity to have both even and odd parity states derived from these. And if you look at the parities of the states that you expect to have here, you can immediately see that actually these band crossings that we have as a function of the out-of-plane momentum are in fact band parity inversions in the system. Now, we also have in this system a threefold rotational symmetry around the c-axis of the material. And it turns out that leads to one of these crossings here being a protected crossing, so being a bulk Dirac point as a function of the out-of-plane momentum. So these states belong to different irreducible representations, and so that crossing there remains protected. But this other crossing is not a protected crossing, and so you'd expect a band gap to open up in these states. And this is then, of course, an inverted band gap where we'd expect some topological states to be living. Okay, so this is of course a very simple picture. This is just thinking about the crystal field levels and the dispersions of these p-derived states. But you see that quite generally from that simple picture, we'd expect to have the formation of both a bulk Dirac point and an inverted band gap hosting topological states in the system. And so we can look for examples of that in the real material now. And if we focus first above the Fermi level here, this is now again in our DFT calculations for palladium ditelluride, you see something rather similar to what I've just been talking about from our simple model. So you can see here the cyan coloring is the PZ-derived state, which is dispersing strongly downwards as a function of out-of-plane momentum here along the gamma ray direction of the Brillouin zone. And you have the red coloring here, which are the PX and the PY-derived states, which have a somewhat weaker dispersion. And these therefore cross over. And you can see exactly as we were discussing in the model, at the top crossing here, you have what seems to be a protected crossing where these bands really cross. And then just underneath that, you have a band gap that opens up. Okay, so this is all very nice in theory, but we want to see this also experimentally, and these states are well above the Fermi level. But if you look down now below the Fermi level, you see a rather similar set of states crossing here. Again, this PZ-derived state disperses down and crosses through the PXY, the top PXY state here. There's then a small inverted band gap beneath that. And then actually in these occupied states, there's another inverted gap down below as the D states start to come into play here as well. And so we can now look for this experimentally. And so I'm showing you on the left here, photon energy dependent ARPAS measurements. So trying to look at the out of plane dispersions of these states. Now, of course, as photo emission is surface sensitive, we have a rather poor KZ resolution, but you can nonetheless still see some features dispersing down here and crossing at this point just about 600 millivolts or so below the Fermi level. And then you see a small band gap opening up below the next set of crossing points here, then with a larger band gap to a 3D dispersing state down here well below the Fermi level. Now, it turns out that in these band gaps, you can see actually some constant spectral weight, so spectral weight that doesn't vary as a function of the out-of-plane momentum. Now, it's very clear in this large band gap. It's a little bit more subtle in this small band gap. But if we look at the in-plane dispersion measurements of these, you can see rather similar features showing up. So if we start near to the Fermi level, well, not that near to the Fermi level, but a few hundred millivolts below the Fermi level, we see that where these states cross and form the bulk Dirac point in the system, we indeed have a Dirac-like feature coming out here. Now you see that this is very filled in, and that's due to the poor KZ resolution of photo emission. And so we have these 3D dispersive states that are forming this bulk Dirac point. Now down here in this large inverted gap, you see a rather clear crossing feature. And so this is a topological state that's located down here well below the Fermi level. And then somewhat more subtly, you can see another crossing state, Dirac state, that's located here in this band inversion where the states hybridize and open a gap. Now this one's a bit more subtle because instead of forming in a well-defined KZ projected band gap, actually this state forms on top of the KZ projection of the bulk bands here. And so you can think of this topological state that forms as a resonance, so a surface resonance, but it's still protected by the topology of the system. And then we have a well-defined topological surface state down below. Now we can see these things in our slab calculations or seed slab calculations as well. And you see we have a really rather excellent agreement between the measured photo emission spectra and these three features that we have in the experiment. And to finally confirm the topological nature of the two surface states that we see here, we can perform spin-resolved photo emission. And you see as we move along these line cuts shown here as A and B, you see you have a very clear spin texture derived from this topological surface state TSS2, with then a similar spin texture that derives from this topological surface state TSS1, which is our surface resonance here. And so really starting from a very simple ingredient, just having these p orbitals dispersing as a function of the out-of-plane momentum, we've generated here a ladder of topological surface states and bulk Dirac points in the system. And so, I mean, this means that the arguments that go into this are really extremely general. This shouldn't be specific just to palladium ditelluride. In fact, we think this basically occurs across the whole of the transition metal dichalcogenide family, where you naturally get this disparate out-of-plane dispersion of the PZ versus the PX and PY states. And just as a brief example of that, these are the measurements that we've been looking at in palladium telluride. But you see very similar things in the sister compound platinum selenide, where we have a bulk Dirac cone and a pair of topological surface states arising in this material. But also in some of the other structural polymorphs, for example, the 2H system, you can see, again, a bulk Dirac cone and now a rather confined topological surface state derived from the same mechanism in that system as well. Okay, and so this is then something that we think is very general across the transition metal dichalcogenides. And I'd like to talk for a few minutes now about how this is actually important to a rather separate topic, the charge density wave instability in titanium ditelluride. Now we've already seen in the last talk actually some very nice measurements of the bulk three-dimensional dispersions of titanium diselenide, and so again it's a system with rather strong out-of-plane dispersions. In this case, we've got a nominally D0 system. So if you just looked at the formal valence of the titanium and the tellurium in the system, you'd expect to find a D0 system with a completely unoccupied titanium conduction band. In actual fact, in this system, these two overlap rather strongly. And so you have now the P states from the valence band crossing the Fermi level and the D states from the conduction band forming a rather deep pocket here at the Fermi level. And these disperse as a function of the out-of-plane momentum. Now, this is the sister compound here to titanium diselenide, and titanium diselenide is a very famous material for a 2x2x2 charge density wave that it hosts in the bulk, and there's been a lot of discussion about the mechanisms of that charge density wave. But in titanium ditelluride, the band overlap near the Fermi level here is much larger than in the selenium compound, and this is thought to completely destabilize the charge density wave instability. And indeed, in the bulk, no charge density wave is seen. But it turns out a rather surprising result from Tai Cheng's group a few years back is that if you take this material and you thin it down to a monolayer, then a charge density wave phase emerges again. And you can see this in our results here from monolayer titanium ditelluride, where at low temperatures, we now see a backfolding of these valence states from the gamma point to the M point of the Brillouin zone, indicating a 2x2 lattice distortion has occurred at low temperatures in this material. And so it's really been a puzzling question for the last few years, why this charge density wave becomes stable in the monolayer case of titanium ditelluride, while it's not stable in the bulk. Now, I should say briefly that the monolayers that we're looking at here are epitaxial monolayers. So we're growing these by molecular beam epitaxy, and all the results I show you for these are on graphene substrates, where these are quite nice van der Waals substrates. So you get a complete relaxation of the lattice constant already for the first monolayer of growth. And you can see this here in reflection high energy electron diffraction measurements. And so we have fully relaxed titanium, well, in this case, selenide, so titanium telluride monolayers, but which still have an epitaxial registry with the underlying graphene substrate. Okay, and so if we take these titanium telluride monolayers, we can look at the temperature-dependent evolution of the electronic structure. And you can see here that as we do that, these backfolded states in the valence band really disappear as we increase the temperature. And so this is another signature that this backfolding is due to a charge density wave instability, and the spectral weight falls off and is basically vanished by, I don't know, 120 Kelvin or so. And so below that temperature, we think we have a charge density wave in the system. Now we can also look at the gamma point, and we see here that in fact we also have a rather strong band reconstruction here, where you can see a slight buildup in the middle here, and you can see this also in energy distribution curves. As we lower the temperature, we have a buildup of spectral weight at the gamma point, which is due to the conduction bands now backfolded from the M point to the gamma point of the Brillouin zone. And actually, if you look in these second derivative measurements, you can see that these backfolded conduction and valence bands appear to perhaps hybridize below the charge density wave transition, as you would expect them to do. And you can see this more clearly if we look at these high resolution measurements. So these are measurements at 106.
5 minutes more.
Perfect, thanks. So these are measurements at 160 Kelvin above the charge density wave transition, and then at 14 Kelvin below the charge density wave transition. And so you can see that as we cool the system down, there's clear band hybridization happening here at the Fermi level, which has been sort of hidden up to now in the spectral broadening that you tend to get in these monolayer systems. And so, you know, this gives us then the first hint of the mechanism for the charge density wave in monolayer titanium telluride, that this band hybridization here is lowering the total electronic energy in the system. And we can try and look at this a bit more quantitatively, and as I'm running out of time, I'll go a little quickly through this, but we can fit the MDC's momentum distribution curves to these spectra. And when we do that, we find clear evidence of band hybridization going on by these dips in the spectral intensity from the fitting. And if you look at a difference plot of these down here, you can see that exactly where the backfolded conduction and valence bands cross at these green and these orange arrows, you get a substantial suppression in the spectral weight pointing to band gap opening. But what's quite interesting in this is that this suppressed spectral weight is rather stronger for the outer crossing than the inner crossing in the system. And that's pointing to some sort of selectivity of the hybridization strength in the system between the different states we have here. So some sort of symmetry selectivity. And in fact, we can understand that on the basis of the p orbital character of these states again. Now, just as for the the palladium telluride that we were talking about, we have px and py derived sets of states giving us dispersive valence bands in the system. And when you have the periodic lattice distortion that accompanies the charge density wave transition, it turns out that only the only the py derived states can couple to this periodic lattice distortion, whereas the px derived states can't couple to this, and so won't hybridize. And if we include this model quantitatively and compare this to our measured electronic structure, you can see that when we take account of this symmetry-based band hybridization in the system, we can really rather accurately reproduce from our model calculations the measured spectra that we see experimentally. Okay, and so we have then a symmetry-selective band hybridization at the charge density wave transition in titanium telluride. And when you look at the associated density of states from this model calculation, you see that there's really a substantial electronic energy gain that can be understood as ultimately as the driving force for the charge density wave transition to happen in monolayer titanium telluride. Okay, so how does all of this compare or relate to the story of band inversions that I was talking about in the first part of the talk? Well, it turns out that if we now look at the case of bulk titanium ditelluride, you can see as a function, sorry, it's a bit in a bit of a pale shading here, but you can see as a function of the out of plane momentum in this system, we have just the same sort of KZ dependent band inversion as we had also in the palladium telluride and the other transition metal dichalcogenides. And one of the things that does is it effectively inverts the ordering of the px and the py dominated states for the inner and outer valence bands in the gamma plane of the system and in the A plane of the system. And when we take all of this into account in our model, so we look at the three-dimensional band dispersions in this system, and we include this switch of the symmetry selectivity of the band hybridizations that you get for the gamma plane and the A plane of the system, it turns out now that if you look at the density of states in the material and compare between the case in orange here, where you have no band hybridization, and in blue, when you turn on an allowed band hybridization, there's really now negligible electronic energy gain near the Fermi level from an associated periodic lattice distortion that if you had one in this system. And so we think ultimately that explains why the monolayer is susceptible to this charge density wave formation, while in the bulk, this driving force, this electronic driving force for the charge density wave to occur is effectively completely removed by the three-dimensional band dispersions, including their out-of-plane band inversions that you have there. Okay, and so I hope then with this, I've convinced you that the transition metal dichalcogenides are rather a nice model system for exploring the effects of out-of-plane dispersions of the PZ versus PX and PY states in the material, and how this can induce various topological band inversions and bulk Dirac states in the materials. We've seen that palladium telluride is a particularly nice case to explore the states that derive from this the topological ladders that derive from this. And we've also seen how this is important to understand the stabilization of a charge density wave in monolayer titanium telluride while it's destabilized in the bulk system. So with that, I'll thank you for your attention, and I'm happy to take questions.
Interest. Professor Bush, yeah, you please go ahead.
Yes. Excuse me. Thank you. Thanks, Phil, for a very nice talk. One thing I didn't quite follow, does the CDW, it seems like the CDW is coupling states like PX to PY or PX to PZ. Is that right? Maybe it's just too early in my time, but
yeah, no, sorry, I went over this a little bit quickly. So what you've really got at the charge density wave transition here is you've got D states, which are forming the conduction bands in the system. These are then backfolded by the 2x2 lattice distortion, and these couple with the P states from the valence bands. And it turns out that if you look in the octahedral coordinate system, you've got X, Y, XZ, and YZ D-derived conduction band states for the three conduction band pockets that are backfolded to the zone center. And then you can ask what's the hybridization matrix elements between those particular D states and the PX and PY derived valence bands. And when you look at that, you find that the PY derived valence band states can couple with, I mean, if we look, for example, for this pocket backfolded to the gamma point, the PY states can couple with the D X prime Y prime states, where the prime is the octahedral coordinate system and the non-primed is the crystal coordinate system. So these can couple when you displace the atoms according to the periodic lattice distortion that you have in the system, whereas the PX derived states can't couple. There's then a combination of a mirror symmetry and a C2 rotation symmetry that prevents that coupling. And so it's really between the D and the P states, but the character of the P states is then dictating which of the band crossings are allowed to hybridize and which aren't.
Okay, thank you.
Thanks.
Please go ahead.
Thank you very much for the interesting talk. Very good data. The situation at L point, could you show again the I think it's last but one slide where you
for the Telluride.
Yeah, this one. Yeah. Well, what's going on in L point actually? Why do you have two features in the bulk material? In
the data here, you mean?
What's your interpretation?
Yeah. So
is it KZ, or why do you have two projections?
So if you look here, the bottom plot is at a photon energy that's nominally probing the L point, and the top plot at a photon energy nominally probing the M point. Our interpretation is that this band here disperses as a function of photon energy or KZ to form this sort of weak minimum here. And the additional spectral weight that we see here is simply a KZ broadening effect. You know, there's a large density of states associated with this little band just below the Fermi level at the M point. And so we see a bit of that in the L point measurements. But if you look at this as a function of KZ, you can see that these states are really moving in and out. The spectral weight's really going in and out. And so I think that's the remnant spectral weight there is just an experimental reality.
Basically the extremes corresponding to the high symmetry points where the dispersion is lower, and that's why when you integrate over KZ.
Exactly, yeah,
Okay.
exactly. So I think you're normally in these spectra, you're normally seeing your spectra dominated by the turning points of the dispersion.
Okay.
Okay, Colin, please go ahead.
Thank you. Very nice talk. So I have two questions. One, in this system itself, this when you look at the spectra from, this one monolayer formed on graphene, I was just curious to know, do you have also some signature of graphene bands visible, because it's a thin layer of this material? So
yes, so we do, but not at the same K point. So if you look at the read here, you see that the lattice constants of I'm showing you titanium selenide here, but it's the same in titanium telluride. The lattice constants of the monolayer are rather different to the lattice constants of the graphene, and because it's van der Waals epitaxy, you grow the monolayer fully relaxed or already in the first layer of growth. And so we do have the Dirac points of graphene that are also visible, but these are just further out in momentum, and so we're not seeing them in the spectra that I showed you here.
Actually, I was curious to know. Okay, my question was mostly like, what is the idea behind using graphene as a substrate for this? Because these are of course interesting materials. The bulk also shows this kind of CDW kind of thing.
So I think in the titanium selenide case, the bulk shows the CDW, although it turns out it's slightly modified in the monolayer limit. In titanium telluride, there's no CDW in the bulk, but you do stabilize a CDW in the monolayer. And so then that's the motivation for going to the monolayer systems for the telluride case.
Is there any, idea behind using graphene instead of some other substrate? Or
yeah, really it's a bit of a Goldilocks substrate, I would say, for these 2D materials, that the interaction between the graphene and the epilayer is sufficiently weak that you're growing fully relaxed. And so it's kind of almost a freestanding monolayer, but there's still just enough of an interaction that you get an epitaxial alignment between the two. So if you look in the lead pattern here, you see that the TMD monolayer is, or at least its Bragg spots are strongly peaked in epitaxial alignment with the graphene. There's a little bit of azimuthal disorder of these still, but it's not too bad. And so it's just kind of a nice balance between enough interaction to get us something that's epitaxial, so then we can study the electronic structure in K-space properly, and a weak enough interaction that we don't think it's strongly perturbing the physics that's going on in the TMD layer.
Okay, maybe I have one more question. Seti, is it okay? I can.
Yeah, because we don't see IV here.
Okay, just on short question. The first system that you have shown, I mean, you have shown this two topological surface states, TSS1 and TSS2. So this TSS1, it was pretty weak in intensity. Is it because of the twinning that you see these two states, or they're coming from the same surface?
No, so they're coming from the same surface. But they're coming from separate band inversions. So there's one band inversion here, one inverted gap here, which gives TSS1, and one inverted gap here, which gives TSS2. This inverted gap you see is a complete KZ projected gap. So there's no bulk states anywhere in here, and so this is then rather clear, and it's clear in the experiment as well.
See, so the intensity variation is because of some matrix element kind.
Well, not really matrix element, I would say, but the one up here is a surface resonance. So here there are KZ projected bulk states, and so the wave function it's still a surface state, but the wave function is more extended into deeper layers below the bulk, and so it's a bit more spread out there, and then it's showing up as a bit weaker in the experiment, and you see a similar thing in the supercell calculations. There's just less wave function weight in the first layer.
Okay, thank you. Thanks.
Professor Sujitha Burman, yeah, please go ahead.
Yes, thank you. It's very nice talk. I have a question that the band crossing between the R4 band and the R5-6 band that you showed, does it get lifted by SOC, or? Does it get lifted by what, sorry? Spin orbit coupling?
No, so this one here is protected against spin orbit coupling by the C3V symmetry that you have in the system. So we think this one here is truly a Dirac point, a bulk Dirac point, whereas the crossing that would have happened down here, this one is lifted by spin orbit coupling, which gives them the inverted gap down here. So so you get both a protected and an unprotected crossing against spin orbit coupling.
Okay. Okay. Another short question, technical. Do you use freestanding graphene for the growth of titanium telluride?
No, we use epitaxial graphene on silicon carbide.
Okay. Okay. Thank you.
Thank you.
Okay. Are there any questions? Okay. Thanks, Phil, for the nice talk. So I have one short question. Maybe I think you may have explained, but this surface state 1 and surface state 2. So why do we need to see resonance? I mean, surface state resonance. Is there some mechanism that we should see surface state resonance here?
So, sorry, I think you're asking about why am I describing TSS1 as a resonance and 2 as a...
Yeah, one is surface state 1 and surface state 2 here.
Yeah, simply because surface state 1 here sits on top of a background of bulk states at some at some KZ, and so it's really a surface resonance in the true sense of a surface resonance versus surface state. The wave function is peaked at the surface, but it extends deeper down into the bulk where it mixes with these bulk states.
Okay.
In contrast, TSS2 is a true surface state in a projected gap, and so the wave function is more localized at the surface.
Okay, since this is surface state, can I understand this like kind of inversion broken symmetry so that we will see two Dirac cones rather than like different way of thinking?
Sorry, that we see two.
This is a surface state. We usually break the inversion symmetry right here. It has no inversion symmetry. This surface state. So
correct.
Then can we usually get two surface states, right? I mean two states if inverse symmetry is broken.
Yeah, I mean, I think you're thinking in a sense about Rashba type states, but I mean here this is a spin polarized Dirac state, so a topological surface state where we just get a single Dirac cone, and you can see from this spin resolved measurement here that you have opposite spin textures on either sides of plus and minus k here, and so this is a single Dirac cone surface state with a chiral spin texture, much like you would get on the surface of bismuth selenide or something like that.
Okay, actually something else is in my mind that, for example, if you see bismuth palladium superconductor. So in the Orpheus rate of bismuth palladium, we do see this kind of like two surface states at the same momentum, one on top another. That's mostly because of inversion symmetry broken. So
no, Seti, I think that's because you have two different kinds of surface. So if you have a twinning, then you can get these states for two different surfaces in your spectrum.
Okay, so
this is not the case here. Yeah,
that's not the case here.
Yeah, because this is a Van der Waals material, and so you get a nice clean surface termination on this. Yeah.
Thanks a lot, Dan. Thanks a lot for the nice talk. So I think we need to find another speaker here. Jaime Barriga should be here, but we don't find him. Jaime, are you there? Are you around? So maybe he's just confused with the timing. I don't know.
Seti, I couldn't find him. I wrote him a message, but he didn't respond. No idea where he is.
Then maybe we take a break then here. Maybe this session has only two speakers.
I'll try to reach him.
Okay. So we have to reschedule his talk. If that is the case.
Anyways, Seti, I think I'll leave maybe in 2 minutes.
Yeah. So you're coming to Kolkata. So welcome to Kolkata.
I'll see you tomorrow.
Yeah, see you tomorrow. So then maybe we'll take a break here now. So let's meet after, I think it's right. So it will be around 5:45 Indian time. Right, in 1 hour from now. Should we shift it? If all the speakers are here, maybe we can shift half an hour. We can shift it forward. So what's the best?
Let's go and schedule that race.
Unscheduled, right? Okay. Okay, then let's take a break and we'll reconvene again at 5:45 p.m. IST, Indian Standard Time. Okay, then. And okay. Thank you all once again for the nice talks. Sergey and Tim. Okay.
Thank you, Seti, for chairing the session. For niceness.
Yeah.
Thank you. Thank you. See you then at 5:45.
5:45.